Why some materials heal themselves while others collapse. Some materials break and never recover. Others crack, pause, and quietly repair themselves. The difference is not magic. It is chemistry deciding who gets a second chance. At first glance, materials seem passive. Steel bends, glass shatters, plastic deforms. We treat damage as final. Once a structure fails, replacement feels inevitable. But nature does not always agree. In biology, damage is often temporary. Healing is built into the system. And chemistry is the reason why. This matters now more than ever. Modern society pushes materials to their limits. Buildings grow taller. Machines run hotter. Devices shrink thinner. Failure becomes expensive, sometimes catastrophic. Understanding why some materials recover while others collapse is no longer academic. It is a question of resilience. To understand this divide, we need to look inside materials themselves, not at shape or strength, but how their molecules respond to stress. When force is applied, bonds stretch. Some snap cleanly, others bend and reform. That difference defines survival. The first narrative beat begins with structure. Rigid materials rely on fixed bonds. Atoms lock into place. This creates strength, but it also creates brittleness. When stress exceeds tolerance, bonds break suddenly. Energy releases all at once. Cracks propagate faster than repair can occur. Collapse follows. In contrast, flexible systems behave differently. Their bonds are reversible. They stretch, rotate, and slide before breaking. Energy disperses instead of concentrating. Damage slows. The system gains time. And time allows chemistry to respond. The second beat follows at the molecular level. Some materials contain mobile components. Polymers that flow. Ions that migrate. Molecules that realign under stress. When damage occurs, these components move toward the fracture. They reconnect broken pathways. What looks like healing is actually reorganization. The third beat reveals intent. Self-healing is not accidental. It is designed into chemistry. Dynamic bonds reform spontaneously. Encapsulated agents release when cracks appear. Environmental triggers activate repair reactions. The material does not resist damage. It manages it. From the outside, this looks like resilience. From the inside, it is constant negotiation between force and flexibility, between order and motion, between breaking and becoming whole again. And this is where the story begins to sharpen, because the same chemistry that allows healing can also create weakness. Not every material can afford flexibility. Not every system benefits from repair. Understanding where the line is drawn explains why some materials survive stress and why others fail the moment it appears. Healing only works when chemistry can move fast enough. That is the hidden constraint. If damage spreads faster than repair, collapse is inevitable. This is where the story deepens. Self-healing materials are not stronger than traditional ones. They are smarter about failure. They accept that damage will happen. Then they design chemistry to respond before cracks grow. At the molecular level, healing depends on mobility. Bonds must break reversibly. Chains must slide instead of snap. Energy must be absorbed, not concentrated. Materials that heal treat stress like information, a signal that triggers rearrangement. Some systems rely on dynamic covalent bonds. These bonds break under stress, then reform when conditions stabilize. The chemistry remembers its original structure. Given time, it rebuilds it. This creates materials that can crack, rest, and recover. Others use embedded healing agents. Microscopic capsules sit dormant inside the material. When a crack forms, capsules rupture. Liquid chemicals flow into the fracture. They react, harden, and seal the gap. The material sacrifices a small region to save the whole. One-time healing, but often enough. Nature uses both strategies constantly. Bone remodels itself. Skin closes wounds. Would redistribute stress along fibers. These systems do not aim for perfection. They aim for continuity, function over appearance. Here is where conflict begins to form. Healing chemistry requires freedom of motion. That freedom reduces rigidity. Rigid materials resist deformation better, but once they fail completely. Healing materials survive longer, but carry lower peak strength. The trade-off is unavoidable. Engineering struggles with this balance. Bridges demand stiffness. Aircraft demand lightness. Medical implants demand compatibility. Each application draws a different line. Too much flexibility invites deformation. Too much rigidity invites fracture. What nobody expects is how environment shapes the outcome. Temperature affects mobility. Moisture activates reactions. Time determines whether repair finishes. A healing material in the wrong environment behaves like a fragile one. Chemistry always needs the right conditions. This is the early tension. Healing is possible, but not guaranteed. And understanding when chemistry can respond becomes the key difference between resilience and collapse. As stress repeats, the difference between healing and collapse becomes sharper. Not all damage is equal, and chemistry does not forgive every kind of force. Repeated stress introduces fatigue. Each cycle stretches bonds again. Each recovery leaves small imperfections. Healing materials can repair cracks, but they cannot always restore original order. Over time, molecular alignment drifts. The system still functions, but margin shrinks. This is where collapse often hides, not in sudden overload, but in accumulated imbalance. Healing slows. Repair becomes incomplete. Cracks begin to outrun chemistry. Once that happens, failure accelerates. Traditional rigid materials face a different fate. They do not heal, but they remain predictable until the end. Engineers can calculate failure precisely. Stress accumulates invisibly, then release is sudden. Clean, catastrophic. Healing systems blur this clarity. Damage disappears, then reappears elsewhere. Strength varies with history. The material remembers stress. Its behavior changes with use. This makes design more complex. Safety margins become dynamic, not fixed. The buildup intensifies here because modern materials increasingly face unpredictable conditions. Vibration, temperature swings, chemical exposure, radiation. Each factor alters healing chemistry. A material designed to recover in one environment may collapse in another. This is why some self-healing systems fail spectacularly, not because the chemistry is wrong, but because the assumptions are. Healing was expected where conditions prevented it. Flexibility was demanded where rigidity was required. The system was asked to be everything at once. Nature avoids this mistake. Bone heals where load is moderate, not where force is constant. Skin repairs where blood flow exists, not where circulation is cut. Biology draws boundaries. Engineering often ignores them. At this stage, the tension peaks, because healing is not a promise. It is an opportunity, one that chemistry may or may not fulfill. And misunderstanding that difference leads to collapse disguised as resilience. The final realization waits here, at the edge between recovery and failure, where chemistry reveals its limits, and materials show us what they were truly built to do. The climax is not repair, it is restraint. Some materials heal because they are allowed to, others collapse because they are asked to endure too much. Chemistry does not promise recovery. It responds to conditions. When stress pauses, bonds reform. When pressure never stops, chemistry gives up. This is the central insight. Self-healing is not strength. It is adaptability. A material that heals is one that can negotiate with damage. It bends rules instead of enforcing them. And that flexibility determines survival more than raw power. The resolution becomes clear when we stop romanticizing healing. Nature does not heal endlessly. It limits activity, redirects force, reinforces weak regions. Healing works because it is paired with restraint. Recovery only happens when damage slows. Modern relevance sharpens this lesson. As materials face harsher environments, smarter design becomes essential. Not stronger, smarter. Structures must expect stress. Devices must allow rest. Systems must include time for chemistry to respond. Without that, no healing mechanism matters. This reframes resilience entirely. Resilience is not resistance. It is recovery capacity. the ability to absorb damage, pause, and reorganize. Materials that collapse fail because they are denied that pause. They are forced past chemistry's ability to adapt. Once you see this, material failure looks different. Cracks are not always defects. They are signals, messages from chemistry about limits. Ignoring them invites collapse. Listening allows survival. Why some materials heal themselves while others collapse is no longer a mystery. It is a choice made at the molecular level, between rigidity and response, between denial and adaptation. And that choice determines whether systems break once or survive stress again and again. Sometimes the smallest shift in perspective becomes the beginning of a new future.